Hello there, and welcome to Sleepy Science Vault. Somewhere above the Earth, beyond the thin blue line of our atmosphere, the sky stops being blue, and starts being something else entirely. Black. Deep. Quiet. And endless, or at least, that's what it looks like. Tonight, we're going to sit with one of the oldest questions human beings have ever asked. Not a question about gods, or meaning, or where we go when we die. A simpler question, in a way. And yet, somehow, an even bigger one. Does space go on forever? It sounds like the kind of question a child might ask, looking up at the stars for the first time. But here's the strange part, scientists still can't answer it. Not because they haven't tried. Some of the most brilliant minds in human history have spent their entire careers staring into this exact mystery. And after all of that effort, after centuries of mathematics, telescopes, satellites, and careful observation, we still don't know, for certain, whether space ends somewhere, or simply continues, without limit, forever. Let that settle for a moment. We can describe the texture of a black hole's event horizon. We can detect light that has been traveling toward us for over 13 billion years. We can map the faint afterglow of the Big Bang itself, spread thinly across the sky like a fossil imprinted in the dark. And yet, with all of that knowledge, all of that extraordinary reach, the basic shape of the universe, its outer boundary, or lack of one, remains hidden from us. What we do know, with complete confidence, is this. Space is bigger than we could ever hope to fully explore. Even if humanity survived for 1,000,000 years, even if we built ships that could somehow approach the speed of light, we would still only ever scratch the surface of what's out there. The observable universe alone, the part we can actually see and measure, is so vast that light from its farthest edges has been traveling toward us since nearly the beginning of time itself. And that's just the part we can see. Beyond that boundary, there could be more stars, more galaxies, more quiet pockets of space, drifting in darkness, that human eyes will never witness, not because they're hidden, but because the light from them simply hasn't had time to reach us yet. Space itself may continue rolling outward, fact after fact, structure after structure, far beyond anything our instruments could ever capture. It's worth thinking about, slowly, the way you might turn over a stone in your hand. In all of recorded human history, in every photograph taken by every space telescope, in every mission we've ever launched beyond our atmosphere, we have never once seen an actual end to space. No wall. No border. No edge where the universe simply stops. Not a single mission, not a single observation, not a single equation has ever revealed the boundary of everything that exists. This absence of an edge isn't proof that one doesn't exist somewhere, far beyond our reach. But it is suggestive. It hints at something. Because if you search long enough, and carefully enough, and you never find a wall, at some point you start to wonder whether the wall is even there to find. The honest scientific answer is this: the possibility that the universe has an end remains completely unknown. Cosmologists, the scientists who study the origin and structure of the universe, have proposed many different models over the decades. Some suggest the universe is finite but unbounded, meaning it has a limited size, but no actual edge, similar to how the surface of a sphere has a limited area but you could walk along it forever without ever hitting a wall. Others propose something far simpler and far more vast. An infinite universe, stretching outward in every direction, without limit, without center, and without end. And here's something that might surprise you. There is no scientific consensus on which of these models is correct. Among the thinkers who study this for a living, the astrophysicists, the cosmologists, the theoretical physicists who spend their lives doing the mathematics of existence itself, opinions remain genuinely divided. This isn't a case where a small group of scientists believe something strange while everyone else has moved on. This is a real, ongoing, unresolved mystery, sitting quietly at the center of modern cosmology. That said, when you ask many scientists privately what they actually believe, based on the evidence available today, a significant number lean toward infinity. They lean toward the idea that space simply continues forever. Galaxy after galaxy. Void after void. Light year after light year, without any final boundary waiting somewhere in the dark. It's a strange thing to sit with. Try to imagine it, just for a moment. Not a large number. Not a number so big it might as well be infinite. An actual infinity. A universe so vast that no matter how far you traveled, no matter how many billions of years you spent moving outward in a straight line, you would never, ever, arrive anywhere close to an edge. Because there wouldn't be one. It's worth saying clearly, this is genuinely possible. Not science fiction. Not speculation dressed up as fact. A real, scientifically defensible possibility, supported by some of our best current models of the cosmos. Space may simply go on. And on. And on. And here's the part that makes this even more compelling. In every direction we have ever looked, using the most powerful telescopes ever built, peering across distances that are difficult to even express in ordinary numbers, we have never detected a wall. We have never detected a border. We have never found some shimmering edge where the universe runs out of space, and something else, or nothing at all, begins. No structure. No boundary marker. No final line in the sand. Just more universe. More stars, more galaxies, more vast stretches of darkness scattered with light, continuing outward as far as our instruments can reach, and likely, far beyond that. This absence of evidence has led most modern scientists to lean toward a particular conclusion. It is considered unlikely, not impossible, but unlikely, that the universe has a physical edge at all. Unlikely that there's some outer shell, some final wall, some cosmic boundary where everything simply terminates. Most current thinking suggests something quieter, and somehow even more astonishing. Space may not be bounded by walls or borders in the way we instinctively imagine. It may simply keep extending, outward and outward, forever folding into more of itself. And if that's true, if outer space is genuinely without limit, then the logical conclusion is almost too large for the human mind to comfortably hold. It means space continues. Forever. Not in the casual way we use that word in daily life, like saying a meeting felt like it lasted forever. We mean it in the truest, most literal mathematical sense. Without end. Without limit. Without final boundary, ever, under any circumstances. Take a moment, here in the quiet, to simply let that idea exist in your mind. You don't have to solve it. You don't have to fully understand it. Scientists themselves haven't fully understood it, not yet, and maybe not ever. Just let it rest there, gently, like starlight settling on still water. Out there, right now, while you lie here listening, space continues. Quietly. Endlessly. Indifferent to time, indifferent to us, simply existing in a way that may have no final edge at all. And somehow, there's something deeply peaceful in that thought. Across a cooling, expanding cosmos, light has been traveling toward us for almost the entire history of existence, arriving here, tonight, as the oldest message anyone has ever received. Let's talk about time. Because to understand how much of space we can actually see, we first need to understand something most people never stop to consider, that seeing into space is also seeing into the past. The universe was born about 13.8 billion years ago. That number is worth sitting with for a moment. Not millions of years. Not even a few billion. Nearly 14 billion years have passed since the moment everything that exists began. Every star, every galaxy, every quiet stretch of darkness between them, traces its origin back to that single, almost unimaginable beginning. And here's something interesting. The universe has a finite age, even if it may have an infinite size. Those two ideas might sound like they contradict each other, but they don't. Age and size are different questions entirely. One asks how long something has existed. The other asks how big it is. And it's entirely possible, even likely, according to many cosmologists, for something to have a clear, measurable beginning in time, while still extending outward in space without any limit at all. Think of it this way. The universe has been expanding for a known, finite amount of time. But that doesn't mean the space it's expanding into, or perhaps more accurately, the space it's expanding has any boundary at all. This single fact, a finite age, is actually the reason we can only ever see a portion of everything that exists. Because light, as fast as it travels, still takes time to cross a distance. And if the universe has only existed for 13.8 billion years, then light has only had 13.8 billion years to travel toward us, from anywhere, in any direction. This creates something astronomers call the observable universe. And its size is almost too large for the mind to comfortably hold. The observable universe stretches about 46 billion light years in every direction from where we stand. Now, you might wonder, how can light only have traveled for 13.8 billion years, and yet the visible distance be 46 billion light years? It feels like it shouldn't add up. But it does, once you remember that space itself has been stretching, expanding, growing larger, the entire time that ancient light was making its journey toward us. The light started its journey from a much closer point. But by the time it finally arrived, here, now, the universe had expanded so much that the source of that light is actually 46 billion light-years away today. So when we look out into the deepest dark, we're not just seeing a fixed snapshot. We're seeing the result of billions of years of cosmic stretching, layered quietly into every photon that reaches our eyes. 46 billion light-years, in every direction. Which means, if you imagine standing at the center of it all, with that distance extending outward equally on all sides, you get a sphere. A vast, glowing bubble of everything we can possibly detect. And the size of that bubble, edge to edge, comes out to roughly 93 billion light-years across. 93 billion light-years. That's the size of the visible universe, the entire stage upon which every star we've ever photographed, every galaxy we've ever mapped, every supernova we've ever recorded, plays out. And yet, here is the quiet truth hiding underneath all of that grandeur. As impossibly vast as 93 billion light-years sounds, the observable universe is definitely finite. It has a size. A measurable, calculable size. It is not without end. It is not infinite. It is, in the truest sense, a bubble, a sphere with very real limits, surrounding us on all sides like the inside of some impossibly large, dark cathedral. This is one of the strange and beautiful tensions at the heart of cosmology. The total universe may be infinite, stretching forever without any edge at all. But the observable universe, the part we can actually detect, measure, and study, is finite. Bounded. Knowable, at least in terms of its size. Beyond that boundary, something important happens. Or rather, something stops happening. Nothing beyond our observable limit can currently be seen. Not because there's nothing there. Not because space ends at that point. But simply because light from beyond that distance hasn't had enough time, in the entire 13.8 billion year history of the universe, to reach us yet. It's a little like sitting in a valley, surrounded by mist, where you can see everything within a certain distance clearly, but beyond that distance, the mist simply swallows everything from view. Not because the world doesn't continue out there. Just because, from where you're standing, you have no way of seeing it yet. Scientists have a specific name for this limit. They call it the cosmic event horizon. It's a beautiful, almost poetic phrase, when you really think about it. A horizon, a boundary beyond which information cannot reach us. Not light. Not radio waves. Not any signal of any kind, from any source, however powerful. Whatever exists beyond that horizon, right now, in this very moment, is, for all practical purposes, unreachable. Unknowable. Sealed away from us not by distance alone, but by the simple, unforgiving relationship between the age of the universe and the speed of light. It's worth pausing on that distinction, because it matters. The cosmic event horizon isn't a wall. It isn't a physical structure sitting out there in space. It's simply the edge of what information has had time to cross. A limit drawn not by geography, but by time itself. And here's something that might surprise you. Even this number, this 93 billion light-year figure, isn't perfectly fixed. As our instruments improve, as our measurements become more precise, scientists periodically refine their calculations. Updated measurements have, in fact, slightly refined the size of the observable universe over the years. Early estimates were a little different. As telescopes grew more powerful, as our understanding of cosmic expansion deepened, the numbers shifted slightly, not dramatically, but enough to remind us that even our best science is a living, evolving thing. Refined again and again, generation after generation, as our tools become sharper and our eyes, in a sense, see further. So we have a number. A real, scientifically grounded number for how much of the universe we can currently observe. 93 billion light-years across. A finite, measurable bubble of stars and galaxies in ancient light. But here's where the truly humbling part begins. Science has no reliable estimate for the size of the entire universe. Not a rough guess. Not an approximate range. No reliable estimate at all. We can tell you, with remarkable precision, how big the observable portion is. But the moment you ask how big the universe is in total, the entire thing, including everything beyond our cosmic horizon, the honest answer from every serious scientist is the same. We don't know. It might be many times larger than what we can see. It might be so large that our observable universe is like a single grain of sand on an endless beach. Or, and this remains a real, live possibility, it might be infinite. Truly, mathematically infinite, with no edge, no boundary, and no final size to ever calculate. The whole universe may be vastly larger than what we can observe. Let that settle here, quietly, in the dark. Everything you've ever seen in a photograph from a space telescope, every galaxy ever mapped, every star ever catalogued, every faint smear of ancient light ever captured by human instruments, all of it, is contained within a sphere 93 billion light-years across. And that entire sphere, as vast as it is, might only be the smallest, faintest fraction of everything that actually exists. We are not looking at the universe. We are looking at our small, local view of it, a single window, framed by time and light, opening onto a structure that may continue, far beyond what any telescope, in any future century, could ever hope to capture. There is something deeply calming in that thought, if you let it settle the right way. We don't need to see all of it to feel its presence. We don't need to measure its outer edge to sense its scale. It is enough, tonight, simply to rest here, beneath a sky that holds more than we will ever know, and let that vastness become, quietly, a kind of comfort. Long before telescopes existed, before anyone understood what a galaxy even was, people would lie outside on quiet nights and ask the exact same question we've been asking tonight. Looking up at all those scattered points of light, they wondered, does this go on forever? We left off with a number almost too large to comfortably picture. 93 billion light-years across, just for the part of the universe we can actually observe. But scientists who study the large-scale structure of the cosmos have pushed even further than that, attempting to estimate what the total universe might look like if we could somehow step outside our observable bubble and measure the whole thing at once. And the numbers they've arrived at are staggering. Estimates suggest the full universe could be at least 250 times larger than the observable region we just described. 250 times. Not twice as large. Not 10 times as large. 250 times the size of that already incomprehensible 93 billion light-year sphere we just spent time exploring. When you actually do that math, when you take our observable bubble and multiply it out to match these broader cosmological estimates, you arrive at a number that starts to lose its meaning the moment you try to picture it. The total universe, by these calculations, could be roughly 7 trillion light-years across. 7 trillion light-years. It's worth saying that number slowly, because the human mind has no natural reference point for it. We can picture a mile. We can stretch our imagination to picture the distance to the moon, or even the sun. But 7 trillion light-years isn't something our minds evolved to hold. It exists only as a number on a page, a result of careful mathematics, describing a reality so vast that large stops being an adequate word for it. And even that number, 7 trillion light-years, may only be a lower estimate. A floor rather than a ceiling. Some models allow for a universe far larger still. Or, as we discussed earlier, a universe with no size limit at all. It's strange to think that human minds, sitting on a small rocky planet, orbiting an ordinary star, in an ordinary corner of one ordinary galaxy among trillions, have managed to calculate numbers like this at all. That we've reached far enough, with mathematics and light and patient observation, to even attempt an estimate of something so far beyond our physical reach. But here's something worth remembering, especially tonight. This question, whether the universe is finite or infinite, whether it has an edge or simply continues forever, is not a new question. It did not begin with modern telescopes, or satellites, or supercomputers running cosmological simulations. People have been asking this question for thousands of years. Long before anyone understood what a star actually was, long before anyone knew galaxies even existed, ancient thinkers looked up at the night sky and wondered about its true size and shape. One of the most influential voices in this ancient conversation belonged to Aristotle. Aristotle, the Greek philosopher whose ideas shaped Western thought for almost 2,000 years, believed the universe had to be finite. Not infinite. Not endless. In his view, the cosmos had a clear structure, with the Earth resting at the center, surrounded by a series of nested, crystalline spheres carrying the sun, the moon, the planets, and finally, the stars themselves. In Aristotle's universe, there was an outer boundary. A final sphere, beyond which nothing existed, not even empty space. To Aristotle, the very idea of true infinity felt logically troubling, almost impossible to reconcile with a universe that seemed orderly, purposeful, and complete. For centuries, this view shaped how people understood their place in the cosmos. A finite, bounded universe, with humanity sitting near its very center. But not everyone agreed. And as centuries passed, as instruments improved, as human curiosity continued pressing outward, new thinkers arrived with new questions. One of the most fascinating came from Johannes Kepler, the brilliant astronomer working in the early 1600s, more than 1,000 years after Aristotle. Kepler argued that stars could not be infinite in number. It's a striking claim, and Kepler's reasoning behind it remains genuinely clever, even today. He noticed something simple, almost obvious once stated out loud, yet profound in its implications. If the universe truly contained an infinite number of stars, scattered endlessly throughout endless space, then no matter which direction you looked, your line of sight should eventually hit a star. Think about that for a moment. If stars are infinite, then looking up at any point in the night sky is like standing in an infinitely large forest. No matter which direction you look, eventually your eyes meet a tree trunk. There are simply too many trees, stretching too far, for any gap to remain truly empty. Kepler reasoned that an infinite universe, filled with stars, should therefore fill the entire night sky with light. Every gap between stars should eventually be filled by yet another star, farther back, and then another behind that one, and another behind that, layer after layer, until the cumulative light from all of them should make the night sky glow brightly. Not dark, scattered with a few thousand visible points. Bright. Practically blazing, from horizon to horizon. But that's not what we see when we look up. We see darkness. Scattered with light, yes, beautiful, twinkling light, but darkness all the same. Vast stretches of black sky between each star, each constellation, each faint smudge of distant galaxy. This contradiction, between what an infinite, star-filled universe should look like, and what we actually observe when we look up at night, became known, centuries later, as Olbers' paradox. It's named after Heinrich Olbers, a German astronomer who explored this puzzle in greater depth in the early 1800s, though Kepler and several others had wrestled with versions of the same question long before him. And it really is a paradox, in the truest sense of the word. A logical puzzle where reasonable assumptions lead to a conclusion that contradicts plain observation. If the universe is infinite, eternal, and evenly filled with stars, the night sky should be bright. And yet, every single night, all across the world, the sky remains dark. Something, somewhere, in that chain of reasoning had to be wrong. For a long time, this paradox simply sat there, unresolved, a quiet thorn in the side of cosmological thinking. Brilliant minds turned it over for generations, offering one explanation after another, none of them fully satisfying. The solution came much later. Centuries later, in fact, with the rise of modern cosmology and our understanding of how the universe actually began. And the answer, once discovered, turned out to be beautifully simple. Almost elegant, in how directly it resolved the puzzle that had confused thinkers for hundreds of years. The universe has a finite age. That single fact, the same fact we explored earlier tonight, turns out to be the missing piece Kepler and Olbers never had access to. Neither of them knew that the universe began, in any meaningful sense, at a specific point in time. They had no concept of a Big Bang, no understanding that the cosmos itself was approximately 13.8 billion years old, rather than eternal and unchanging. And once you know the universe has a finite age, the paradox unravels almost effortlessly. Light from extremely distant stars simply hasn't had enough time to reach us. Even if the universe contains a truly staggering number of stars, even if it stretches on, possibly without any limit at all, exactly as we discussed earlier, the light from the most distant of those stars has not had enough time, in 13.8 billion years, to travel all the way here. Kepler and Olbers were imagining a universe that had existed forever, stretching infinitely backward in time as well as infinitely outward in space. In a universe like that, yes, light from every star, however distant, would eventually arrive, filling the sky with brightness. But that's not the universe we actually live in. Our universe had a beginning. A starting point, sharp and definite, sitting 13.8 billion years behind us. And because of that beginning, only the light that has had time to reach us, light from stars within that 46 billion light-year observable radius we discussed earlier, has actually arrived. Everything beyond that distance remains dark to us, not because it doesn't exist, but simply because its light is still traveling, slowly, patiently, making its way across distances so vast that human timescales barely register against them. That's why the night sky remains dark. It's a quietly beautiful resolution, when you really sit with it. The darkness above us, the very thing that makes stargazing peaceful rather than blinding, is itself a kind of message. A signature, written across the sky, revealing that the universe had a beginning, that time itself has a starting point, and that we are still, even now, receiving its earliest letters, one photon at a time. So the next time you find yourself outside on a clear night, looking up at that familiar scattering of stars against deep black sky, remember that the darkness between them isn't empty in the way it seems. It's simply unfinished. It's space still waiting for old light to arrive, a story still being delivered, slowly, across billions of years, to anyone patient enough to look up and receive it. After Olbers' paradox finally found its quiet resolution, science didn't stop asking questions. If anything, the questions only became stranger and more wonderful. Because once thinkers accepted that the universe had a beginning, a new mystery quietly took shape, not about time anymore, but about the very nature of space itself. For that, our story moves forward, into the work of one of history's most towering scientific minds. Isaac Newton, working in the late 1600s, gave the world a vision of space that felt, in many ways, like simple common sense. Newton imagined space as something fixed, unchanging, a vast, infinite stage upon which all the events of the universe played out. In Newton's view, space was like an enormous, empty container, stretching endlessly in every direction, never bending, never moving, never changing its basic shape. Stars and planets move through this container, influenced by gravity, following predictable mathematical laws. But space itself, the container, simply was fixed. Absolute. The same yesterday, today, and forever. It's an intuitive idea, honestly. It matches how space feels to us, in everyday experience. The room you're resting in right now feels fixed. Distances feel constant. A mile today feels the same as a mile tomorrow. For more than 200 years, Newton's vision of space dominated scientific thinking. It worked beautifully for calculating the orbits of planets, the trajectories of comets, the motion of falling objects. It was, by almost every practical measure, an extraordinarily successful idea. But then, in the early 20th century, everything changed. Modern physics revealed something Newton could never have imagined. Something that would have seemed, even to his brilliant mind, almost like science fiction. Space itself can bend. It's worth pausing on that sentence, because it really is one of the strangest, most counterintuitive discoveries in the history of science. Not objects moving through space. Not light traveling along a path. Space itself, the very fabric Newton imagined as fixed and absolute, can curve, stretch, and warp. This discovery came from Albert Einstein, whose work in the early 1900s completely reshaped how scientists understand reality. According to Einstein, gravity is not simply a force pulling objects toward each other, the way Newton had described it. Gravity, in Einstein's revolutionary vision, is actually a curvature. Massive objects, stars, planets, black holes, don't just pull on space from a distance. They actually bend the fabric of space around themselves, the same way a heavy ball placed on a stretched sheet of fabric creates a dip, a curve, a gentle valley in the material itself. Gravity curves the fabric of space. When a planet orbits a star, it isn't simply being pulled by some invisible force reaching across empty distance. It's actually following the natural curve of space itself, like a marble rolling along the curved surface of that stretched fabric, tracing a path shaped entirely by the geometry around it. This single idea, that space can curve, bend, and warp, opened a door to questions Newton's flat, fixed universe never could have allowed. Because if space can curve, what shape might the entire universe actually have? This is where Einstein's work led to one of the most beautiful, mind-expanding ideas in the history of cosmology. Einstein showed that space could be finite without having an edge. Take a moment with that idea, because it sounds, at first, almost like a contradiction. How can something be finite, limited, measurable, with a definite size, and yet have no edge, no boundary, no final wall where it simply stops? The answer lies in curvature. Imagine, for a moment, the surface of a sphere. Not the solid ball itself, just the outer surface, the curved skin wrapping around it. That surface has a finite size. You could, in theory, measure its total area in square miles, or square light years, or any unit you like. It is not infinite. It has a clear, calculable size. And yet, if you were a tiny creature, walking along that surface, you would never, ever encounter an edge. No matter which direction you walked, no matter how far or how long you traveled, you would simply keep moving, and moving, and moving, across a surface that curves gently beneath your feet, with no wall, no boundary, no edge ever appearing before you. A finite universe could resemble exactly this kind of curved surface. Not flat, like the endless tabletop Newton imagined. Curved. Gently bending back upon itself, in a way human intuition struggles to picture, but mathematics can describe with complete precision. In a universe shaped this way, you might travel forever, in a straight line, by every local measurement, without ever encountering a boundary. No wall. No edge. No final point where space runs out. And here is the part that tends to genuinely astonish people, the first time they really understand it. In a universe curved this way, eventually, you could return to where you started. Imagine setting off from Earth in a spacecraft, traveling in a perfectly straight line, never turning, never deviating, simply moving forward through space for an unimaginably long time. In a curved, finite universe, that straight line wouldn't extend forever into emptiness. It would gently curve, following the underlying geometry of space itself, and after an inconceivably vast journey, you might find yourself arriving, quite literally, back where you began. Not because you turned around. Not because you circled back deliberately. Simply because the space you were traveling through was curved in such a way that straight eventually, gently, led home. It's a strange and beautiful idea, almost poetic in its symmetry. A universe where there is no edge defined, and yet the whole thing remains finite, measurable, complete. This single insight transformed how scientists think about infinity itself. Before Einstein, the only way scientists could imagine a universe without an edge was to imagine a universe that was simply infinite, stretching outward forever, without any limit to its size. Finite and edgeless seemed like a contradiction, almost a logical impossibility. But curvature changed everything. It revealed a third option, hiding quietly between the two extremes people had always assumed were the only possibilities. Not simply finite with an edge. Not simply infinite without one. But something far more elegant. Finite, and yet, somehow, completely boundless. Space, according to this model, could be finite but borderless. Limited in total size, yet containing no boundary anywhere within it. No wall waiting at the outer reaches. No edge for any traveler, in any spacecraft, to ever discover. It's a difficult shape to picture, honestly, because human minds evolved to understand flat surfaces and straight lines, not curved, higher-dimensional geometries bending back upon themselves in ways our everyday experience never prepares us for. Which is why scientists, when trying to explain this idea to the rest of us, often turn to a simple, gentle analogy. One that has helped generations of curious minds begin to grasp something that mathematics alone makes difficult to visualize. The balloon analogy. Picture, for a moment, the surface of a balloon, not the air inside it, just the thin, stretchy material of its outer skin. Now imagine drawing small dots all across that surface, scattered randomly, representing galaxies. As you slowly inflate the balloon, something interesting happens. Every dot moves farther away from every other dot. The surface itself stretches, expanding outward in every direction, carrying the dots along with it. And yet, no matter how large the balloon grows, no matter how far those dots drift apart, none of them ever reaches an edge. There is no boundary anywhere on that curved surface. No corner. No outer rim where the balloon's skin simply stops. The surface is finite. You could calculate its exact area at any given moment. And yet it is also, in its own two-dimensional way, completely borderless. This is, in a gentle and simplified way, something like what Einstein's mathematics suggests might be true of our actual universe, not in 2 dimensions, like a balloon's surface, but in 3, curved through a kind of geometry that's almost impossible to directly visualize, yet perfectly describable through careful mathematics. It's worth resting on this image for a while, here in the quiet. A universe that may have no edge anywhere within it, and yet might still, technically, be finite. Curved so gently, so vastly, that no traveler, no light beam, no signal of any kind would ever encounter a wall. Just space, continuing on, curving softly beneath everything that exists, leading, perhaps, not towards some distant boundary, but quietly, eventually, back toward home. Let's continue exploring the idea we left off with, a universe that curves so gently, so completely, that travel could continue endlessly within it, without ever once meeting an edge. This isn't just a beautiful metaphor borrowed from a balloon's surface. It reflects something scientists take seriously when they model the actual shape of our universe. The universe may wrap back on itself. This is one of the genuine possibilities still on the table in modern cosmology, not science fiction, not speculation for its own sake, but a real mathematical model that fits within the framework of Einstein's equations. A universe where space curves so completely that, if you continued traveling in a single direction for long enough, you wouldn't fly off into some infinite void. You would, instead, slowly find yourself approaching your own starting point again, having circled the entire shape of space itself. It helps to think of something far more familiar, something every one of us has experienced in a much smaller way. Like traveling around Earth, you might never encounter an edge. Imagine standing on the surface of our planet, completely unaware that it's round. If you simply started walking, and kept walking, in what felt like a perfectly straight line, you would never bump into a wall. You'd never reach some sudden cliff marking the end of the world. You'd simply keep walking, day after day, across oceans and continents, curving gently along with the planet's surface, until, eventually, you arrived back exactly where you started. Not because you turned around. Simply because the ground itself was curved, gently, invisibly, beneath every step you took. The universe, according to certain cosmological models, might behave in exactly the same way, just at a scale so vast that the comparison becomes almost impossible to fully picture. Not curving in 2 dimensions, like Earth's surface, but curving in 3, through space itself. And here's something worth pausing on. Even if the universe did end, in the sense of being a closed, complete, finite shape, it might still curve endlessly. Those 2 ideas, finite and endless, sound like they should cancel each other out. But they don't. Not in this kind of geometry. A finite universe can still appear endless. This is one of the most quietly profound ideas in all of cosmology, and it's worth letting it settle slowly. A universe could have a definite, measurable, finite size, and yet, from the perspective of anyone actually living inside it, traveling through it, exploring it, it would feel completely without limit. Endless, in every practical sense, even while being technically finite in its underlying structure. No traveler would ever reach a wall. No probe, sent outward in any direction, would ever return data showing some final boundary. Everything would simply continue, curving gently, leading eventually back toward where it began, but never, at any point along the journey, presenting anything that felt like an ending. Scientists have a specific term for universes shaped this way. They call them closed universes. and closed universes allow endless travel without boundaries. It's a strange phrase to really absorb. Closed, and yet endless. Bounded in total size, and yet boundless in actual experience. It captures, in just a few words, one of the most elegant truths to emerge from modern physics. A universe doesn't need to be infinite to feel infinite. It simply needs to be curved in the right way. So what determines whether our universe is actually shaped like this? What decides whether space curves back on itself, creating this closed, finite, yet boundless structure? The answer lies in something called curvature, a concept that sits at the very heart of Einstein's equations. Positive curvature would make space finite. This is the specific geometric shape that creates a closed universe, the kind we've been describing, the kind where straight-line travel eventually loops back on itself, the kind built from the same underlying logic as that balloon analogy, or the surface of Earth itself. When space possesses what physicists call positive curvature, it behaves like the surface of a sphere, gently curving inward on itself in every direction, ultimately producing a finite, closed shape. But positive curvature isn't simply a philosophical possibility. It's something tied directly to a measurable physical quantity, the overall density of matter and energy contained within the universe. If density exceeds a critical value, the universe would be closed. This critical value, sometimes called the critical density, represents a kind of cosmic tipping point. If the universe contains more matter and energy than this critical threshold, gravity's combined pull becomes strong enough to curve the entire fabric of space back upon itself, creating exactly the kind of closed, positively curved universe we've been exploring tonight. In a universe like this, the combined gravitational influence of everything that exists, every star, every galaxy, every cloud of cosmic gas and dust, every trace of dark matter scattered invisibly throughout the void, would be powerful enough to bend the overall geometry of space into a closed shape. And such a universe would have no edge, despite having a finite volume. It's worth letting these words rest together for a moment, because individually they sound contradictory, and yet together they describe something mathematically coherent, even beautiful. No edge. And yet, finite. A complete, measurable, calculable amount of space, that nonetheless contains no boundary anywhere within it, for any traveler to ever discover. This is the strange and wonderful possibility currently sitting within the range of serious scientific models. Not certainty. Not proof. But a genuine, mathematically consistent option for what our universe might actually be. Of course, this is only one possible shape among several. And to really understand the full picture, it helps to step back and consider the broader questions scientists ask when trying to determine the universe's true structure. Geometry and topology determine the universe's true shape. These are two related but distinct ideas, both essential to understanding how cosmologists think about the architecture of everything that exists. Geometry refers to the local curvature of space, whether space, at any given point, curves inward like a sphere, curves outward like a saddle, or remains essentially flat, the way Newton once imagined it. Geometry tells us how space behaves, how parallel lines interact, how angles and distances relate to each other across the fabric of the cosmos. Topology, on the other hand, is a slightly different question. It asks about the overall connectedness of space, how different regions link together, whether space wraps around on itself, whether there might be hidden connections folding distant regions closer together than they initially appear. Together, geometry and topology form the complete mathematical description of the universe's true shape, not just how space curves locally, but how the entire structure connects, extends, and potentially closes back upon itself across the largest scales imaginable. And these two properties, working together, create several genuinely distinct possibilities for what our universe might actually be. We've already explored one of them tonight, a closed universe, shaped by positive curvature, finite in volume yet endless in experience, much like the surface of a sphere extended into 3 dimensions. But there's another major possibility, one that current observations actually suggest might be closest to our own universe's true shape. Flat universes can be finite or infinite. This is a subtle and fascinating point, because it reveals something that often surprises people the first time they encounter it. A flat universe, meaning a universe where space follows the same basic rules of geometry most of us learned in school, where parallel lines never meet, where the angles of a triangle always add up to exactly 180 degrees, doesn't automatically tell you whether that universe is finite or infinite. Flatness describes local geometry, how space behaves, region by region, at the level we can directly measure and test. But it says nothing, by itself, about the overall global shape of the universe, about whether that flat geometry extends infinitely in every direction, or whether it wraps around, through some more complex topology, into a finite, though still flat, overall structure. It's a little like that flat piece of fabric we imagined earlier, except now picture it being capable of 2 very different fates. In one version, the fabric simply continues forever, flat and unbroken, stretching outward without any limit at all. In the other version, that same flat fabric gets connected at its edges, rolled gently into a cylinder, or folded into more complex shapes, creating a finite total area, while still remaining, at every individual point, perfectly flat. Both possibilities are mathematically valid. Both are consistent with everything we currently observe about the geometry of our universe. And remarkably, our best current measurements suggest that the universe, on the largest scales we can detect, does appear to be remarkably flat, very close to that critical density we discussed a few moments ago, the precise tipping point between a closed, finite universe, and something else entirely. But flatness alone doesn't resolve our original question. It simply adds another layer of complexity, another reason why the true answer, finite or infinite, continues to elude even our most careful, most patient scientific investigations. So we find ourselves, once again, standing at the edge of human knowledge, not because scientists haven't tried hard enough, or thought carefully enough, but because the universe itself seems to have built genuine ambiguity into its own structure, hiding its true shape behind measurements so subtle, so delicately balanced, that certainty continues to slip just beyond our reach. And yet, there is something undeniably peaceful in that uncertainty, if you allow yourself to simply rest within it tonight. We may never know, with complete certainty, whether our universe closes gently back upon itself like the surface of a sphere, or extends outward forever, flat and endless, into infinite space. But either way, whichever shape it ultimately turns out to be, it continues. Quietly. Patiently. Curving, or stretching, or perhaps doing both, in ways still hidden from us, carrying within it every star, every story, every quiet moment of rest, including this one, here, now, as the universe goes on being whatever vast, beautiful shape it has always been. There's another shape worth considering tonight, one that curves in the opposite direction from the closed universe we explored a moment ago. Where positive curvature folds space inward like the surface of a sphere, there exists a kind of geometry that does precisely the opposite, curving outward, endlessly, like the surface of a saddle stretching in every direction at once. This is called negative curvature, or sometimes, hyperbolic geometry. And it leads us toward another genuine possibility for the true shape of our universe. Negatively curved universes can also be infinite. Unlike the closed, positively curved universe we discussed earlier, a universe shaped by negative curvature doesn't fold back on itself. It doesn't create that gentle, sphere-like loop where a traveler eventually returns to their starting point. Instead, it does something closer to what Newton originally imagined, though through a far stranger, more complex geometry than he ever could have pictured. It simply continues outward, in every direction, without limit. A simply connected flat universe would continue forever. This phrase, simply connected, is worth pausing on, because it carries real mathematical weight. It means a universe with no hidden loops, no folded connections linking distant regions back to one another, just space, extending outward, plainly and directly, the way most of us instinctively imagine when we picture infinite space for the first time. A flat, simply connected universe wouldn't curve back on itself in any way. It would simply keep going, in every direction, forever. And remarkably, the same turns out to be true for that other kind of curved space we just introduced. A simply connected hyperbolic universe would also continue forever. Even though hyperbolic space curves, bending outward, the way a saddle curves away from its center, a simply connected version of this geometry still produces an infinite universe. No loops. No folding back. No eventual return to a starting point. Just endless expansion, outward, through a geometry far stranger and more difficult to visualize than the gentle curve of a sphere, yet infinite all the same. So here we have two distinct shapes, flat space, and negatively curved hyperbolic space, that, in their simplest, most straightforward form, both lead to the same ultimate conclusion. An infinite universe, with no edge, and no return. But here's where the story takes an unexpected turn, because it turns out that flatness, even though it can produce an infinite universe, doesn't always have to. Flat space may still possess finite topologies. This is one of the more delicate, mathematically rich ideas in modern cosmology, and it's worth slowing down to really absorb it. Even though flat space, left entirely on its own, naturally extends forever, it's mathematically possible to take that same flat geometry, and connect it, fold it, or loop it back upon itself, through more complex topological structures, creating a universe that is flat in its local geometry, and yet still finite in its overall size. It sounds almost paradoxical at first. How can something be flat, the same flatness that naturally implies endlessness, and yet still be finite, bounded in its total extent? The answer lies in topology, that idea we touched on earlier, describing how different regions of space connect to one another, beyond simply how they curve. And remarkably, scientists have actually cataloged the possibilities. Scientists have identified 18 distinct finite topological possibilities for a flat universe. 18. Not an infinite range of vague, hand-wavy options, but a precise, mathematically defined set of 18 distinct ways that flat space could be folded, connected, or looped in on itself, while still producing a universe with finite total volume. It's remarkable, honestly, that mathematics allows for this kind of precision. That out of all the seemingly endless ways one might imagine folding three-dimensional space, only 18 distinct, finite, flat possibilities actually emerge from the underlying equations. One of these 18 possibilities is particularly easy to picture, at least compared to the others. It's called a three-dimensional torus. A torus universe resembles a cosmic donut. Now, this doesn't mean the universe would visually look like a donut, with a hole in the middle that you could photograph from some outside vantage point. It means the underlying connectivity of space would behave the way a donut's surface behaves, a shape mathematicians find wonderfully useful, precisely because it's finite, yet contains no actual edge. Think back, for a moment, to a simpler, two-dimensional version of this idea, something many of us have actually experienced without even realizing it. Old video games, the simple ones from decades ago, sometimes built their worlds this way. If your character moved off the right edge of the screen, they would instantly reappear on the left edge. Move off the top, and you'd reappear at the bottom. That simple design choice was, mathematically speaking, exactly a torus. A flat, finite space, with no actual edges anywhere within it, simply because the opposite sides loop around and connect to each other, invisibly, behind the scenes. Travel far enough in any direction, and rather than hitting a wall, or simply continuing forever into infinite emptiness, you'd eventually find yourself arriving back where you started, having quietly looped around the entire connected structure of that finite space. A three-dimensional torus universe would work the same way, just extended into one additional dimension. Travel far enough in any direction, forward, sideways, even upward or downward, and you would eventually loop back, arriving once again at your starting point, having journeyed across the entire finite extent of a universe that nonetheless contains no detectable edge anywhere within it. It's a genuinely strange, almost playful idea, when you really let it settle. The universe, behaving a little like an old video game world, looping, connecting, wrapping around itself in ways invisible to anyone living quietly within it. And the torus is just one of those 18 possibilities. The others involve even more complex, more difficult to visualize topologies, mathematical structures that fold and connect three-dimensional space in ways that resist simple, comfortable mental pictures, yet remain perfectly valid, perfectly consistent with the underlying laws of physics as we currently understand them. This same idea, folding space into finite, edgeless structures, does it only apply to flat universes? It applies to curved universes too. Closed flat and hyperbolic models are multiply connected. This phrase, multiply connected, stands in direct contrast to the simply connected universes we discussed a few moments ago, where simply connected spaces extend outward without any folding or looping. Multiply connected spaces involve exactly that kind of folding, regions of space connecting back to other regions, through pathways that aren't immediately obvious, creating finite structures out of geometries that would otherwise naturally extend forever. And these multiply connected models, whether built from flat geometry, or from that stranger, outward curving hyperbolic geometry, produce something fascinating. They produce finite but unbounded universes. Finite in their total size, measurable and calculable, just like that closed, positively curved universe we explored earlier. And yet, simultaneously, unbounded, containing no actual edge, no wall, no final boundary that any traveler, in any direction, could ever discover. It's remarkable how many different mathematical paths seem to lead toward the same, recurring idea throughout tonight's exploration. Finite, yet edgeless. Bounded in total extent, yet endless in lived experience. Whether through the simple, elegant curve of a sphere, or through the more exotic folding of a flat or hyperbolic torus, the universe keeps offering us this same strange, beautiful possibility, again and again, through different mathematical doors. So where does this leave us, after exploring flat universes, curved universes, simply connected possibilities, and these intricate, multiply connected topologies? It leaves us, honestly, in the same place modern cosmology actually finds itself today. Current measurements fit both finite and infinite possibilities. This is the genuinely humbling truth sitting underneath everything we've explored tonight. Despite generations of careful observation, despite satellites measuring the faint afterglow of the Big Bang with extraordinary precision, despite mathematicians cataloging every possible topology with remarkable rigor, our actual data, the real measurements taken from telescopes and satellites, remains consistent with both an infinite universe, stretching forever without limit, and a finite universe, curving or folding back upon itself in one of these many possible ways. The evidence simply doesn't, yet, point decisively toward one answer over the other. It's a strange place for science to stand, in some ways. We possess almost unimaginably precise tools. We can measure cosmic background radiation to accuracies that would have seemed like magic just a century ago. And yet, this most fundamental of questions, finite or infinite, remains genuinely, honestly open. Perhaps that's not a failure of science, though. Perhaps it's simply an honest reflection of how vast, how subtle, how quietly mysterious the universe actually is. So tonight, as you rest here, in the dark, surrounded by all of these possibilities, a closed universe curving gently back upon itself, a flat universe extending forever in every direction, a hyperbolic universe stretching outward through strange, saddle-shaped geometry, or perhaps some intricate, folded topology, finite yet edgeless, looping quietly through dimensions we can barely picture. Know that all of these remain genuinely, scientifically possible. The universe holds its true shape close, for now, patient, vast, and quietly unwilling to reveal, just yet, which of these beautiful possibilities it has actually chosen to become. If the universe really does loop back on itself, the way we explored in that strange, donut-shaped torus a moment ago, then something rather remarkable should follow from it. Something testable. Something astronomers could actually search for, using nothing more exotic than light itself, and a great deal of patience. If space loops, light could travel around the universe. This is where the idea stops being purely theoretical and starts becoming something scientists can genuinely investigate. Because if the universe truly is finite, and truly does fold back on itself through one of those intricate topologies we discussed earlier, then light, just like a traveler walking the surface of the Earth, would eventually circle all the way around, returning to where it began. And light moves fast. Unimaginably fast, by any human standard. Which means, given enough time, it wouldn't just complete that loop once. Light might circle space more than once. Picture a single beam of light, released from some ancient galaxy, billions of years ago. In an infinite universe, that light simply travels outward, forever, never returning, never repeating its journey. But in a finite, looped universe, that same beam of light could complete its circuit around the entire cosmos and, astonishingly, begin the journey all over again. Looping. And looping again. Potentially, over vast enough timescales, many times over. And if light can loop around space more than once, then something curious should happen to the things that light comes from. Multiple images of galaxies could appear. Think about what this actually means. If light from a single galaxy can travel all the way around a finite, looped universe, then that same light, having completed its journey, could arrive back at its starting point, and continue past it, traveling around again. Which means, from our vantage point here on Earth, we might not just see that galaxy once. We might see it multiple times. The same galaxy, appearing in completely different parts of the sky, its light having taken different paths, different routes around the looping structure of space, arriving at our telescopes from entirely different directions, yet originating from the exact same source. We might see cosmic duplicates. It's a wonderfully strange idea, when you really sit with it. Somewhere out there, scattered across the night sky, in regions that appear, at first glance, to be completely unrelated, there could be repeated images of the same ancient galaxy. Like looking into a hall of mirrors, except built from light itself, stretched across billions of years and unimaginable distances, with each reflection representing one more loop around the hidden shape of the cosmos. And this leads to something genuinely profound about how a finite universe might actually appear to us, even if it isn't infinite at all. The universe could look infinite, even if it isn't. This is worth sitting with for a long moment, here in the quiet, because it touches something deeply philosophical, hidden just beneath the surface of the mathematics. If light loops around a finite universe enough times, creating enough overlapping duplicate images, scattered across enough different directions, the sky could become so densely filled with repeated galaxies, repeated stars, repeated structures, that it would become essentially impossible, just by looking, to tell the difference between a genuinely infinite universe and a finite one, looping back on itself so many times that its repetitions blur together into something that feels endless. In other words, a small, finite universe, given enough time and enough loops of light circling endlessly through its structure, could disguise itself, almost perfectly, as something infinite. It's a quietly humbling thought. The vastness we perceive, simply by looking up at a sky scattered with what seems like countless, never-repeating stars and galaxies, might not actually reflect genuine infinite scale at all. It might, instead, reflect a finite universe, wearing infinity's reflection across its own folded, looping structure. This particular kind of repetition has a specific signature, especially in that toroidal universe we discussed earlier, the cosmic donut shape, looping space back on itself in a particularly structured, mathematically predictable way. A toroidal universe would create mirror-like repetitions. Not random duplicates, scattered chaotically across the sky. Structured ones. Patterned ones. Repetitions that would follow the precise mathematical rules of the torus's underlying geometry, creating what scientists sometimes describe as a kind of cosmic hall of mirrors, distant galaxies appearing again and again in predictable positions, following the hidden symmetry of space's true, looping shape. And here's the truly remarkable part of this story. This isn't simply a beautiful theoretical possibility, left untested, sitting quietly in academic papers, never actually investigated. Astronomers have searched for such duplication. Real scientists, using real telescopes, have actually gone looking for this exact pattern, scanning the deepest, most distant regions of observable space, searching specifically for repeated galaxies, repeated structures, repeated patterns in the faint background radiation left over from the Big Bang itself, hoping to find this signature of a looping, finite universe. It's a genuinely creative piece of scientific detective work, when you think about it. Rather than trying to directly measure the edge of the universe, an impossible task, as we explored earlier tonight, scientists instead searched for an indirect signature. A clue, hidden in patterns of repetition, that would reveal a finite, looping structure, even without ever directly observing any actual boundary. Researchers studied the cosmic microwave background, that faint, ancient afterglow of radiation left over from the universe's earliest moments, searching specifically for matching patterns, appearing in different parts of the sky, that might reveal space looping back upon itself. They searched carefully, patiently, using some of the most sophisticated instruments ever built by human beings. And so far, none has been conclusively found. No matching pairs of galaxies, confidently identified as cosmic duplicates. No clear repeating patterns in the cosmic microwave background, definitively proving that space loops back on itself. No conclusive evidence, of any kind, supporting the toroidal, looping universe we've spent the last few minutes exploring. This doesn't mean such a universe is impossible. It simply means, with our current technology, with our current depth and precision of observation, no one has yet found the specific signature that would prove it. And there's another piece of evidence, closely related to this search, that adds a bit more weight to one side of this ongoing mystery. Observations suggest light does not appear to wrap around space. This is a slightly broader finding than the search for duplicate galaxies specifically. It reflects a wider pattern of observation across many different studies, all generally failing to find the kind of repeating, looping signatures that a small, finite, wrapped universe should, in theory, produce. If the universe really were small enough and looped enough times, we should expect to see clear, unmistakable evidence of that looping by now, not just occasionally, in obscure corners of the data, but clearly, consistently, across multiple independent lines of observation. And that clear, consistent evidence simply hasn't appeared. This slightly favors an infinite interpretation. It's important to say this carefully, gently, the way scientists themselves tend to phrase it. This isn't proof. It isn't certainty. It's a slight lean, a gentle tilt in the evidence, suggesting that if the universe does loop back on itself, the way that torus model describes, it would have to be so enormous, so vastly larger than our observable universe, that any looping signature would be effectively invisible to us anyway, hidden beyond even our cosmic horizon. Which means, even this search, this beautiful, careful, creative attempt to find cosmic duplicates scattered quietly across the sky, still leaves us, ultimately, without a definitive answer. Just like every other approach we've explored tonight, this one too dissolves, gently, into the same humbling truth that's been resting quietly underneath this entire journey. We have searched. Carefully. Patiently. Using every tool human ingenuity has managed to construct. And the universe, vast, quiet, and endlessly patient itself, continues to hold its answer close, just beyond our reach, leaving us, tonight, exactly where we began. Wondering. Searching. And somehow, in that very uncertainty, finding a strange, quiet kind of peace. There's a discovery that changed everything we just spent the last hour exploring, a discovery so fundamental that, without it, none of the models we've discussed tonight would even make sense. It begins not with a question about shape, or edges, or curvature, but with a much simpler observation. The universe is moving. The universe has expanded since the Big Bang. This is one of those facts so foundational to modern cosmology that it's easy to forget how genuinely shocking it once was. For most of human history, the night sky seemed fixed. Eternal. Unchanging. The stars our ancestors saw were assumed to be the same stars, in the same positions, that their ancestors had seen before them, stretching back through countless generations. But in the early 20th century, astronomers discovered something that quietly dismantled that assumption forever. The universe was not static. It was not standing still. From the very moment of its birth, 13.8 billion years ago, it has been expanding, growing larger, continuously, every single moment since. And the way this expansion actually works is far stranger, and far more beautiful, than most people initially imagine. Space itself expands between galaxies. This distinction matters enormously, and it's worth sitting with for a moment. The expansion of the universe isn't simply galaxies flying outward through space, the way debris might scatter outward from an explosion. It's something subtler, and somehow even more remarkable. The space between galaxies is itself growing. stretching, expanding, quietly and continuously, carrying galaxies along with it, the same way those dots on the surface of our balloon drifted apart, not because they were moving across the balloon's surface, but because the surface itself was stretching beneath them. Galaxies, for the most part, aren't racing through space under their own power. They're being carried, gently and inexorably, by the expansion of space itself. And because of this, something quietly remarkable happens to every galaxy in the universe, given enough time. Galaxies move farther apart over time. Not because they're fleeing from each other, in the way that phrase might suggest. Simply because the space separating them keeps growing, moment by moment, year by year, like that fabric continuing to stretch long after we stopped watching it. This creates a pattern that astronomers have measured with remarkable precision, and it reveals something rather elegant about how this expansion actually behaves across the cosmos. More distant galaxies recede faster. This might seem strange at first. Why would distance affect speed? But once you remember that it's the space itself doing the stretching, rather than the galaxies actively moving, the pattern starts to make beautiful sense. A galaxy that's twice as far away has twice as much space between it and us, and so twice as much space is expanding, simultaneously, along that entire distance. Which means that galaxy appears to recede from us roughly twice as fast. The farther away something is, the faster the space between us, and it seems to be growing. It's a relationship astronomers call Hubble's law, named after Edwin Hubble, the scientist who first carefully measured and documented this pattern in the 1920s, a discovery that quietly launched modern cosmology into existence. And here's where this idea begins to challenge something many people instinctively assume, the very first time they hear about cosmic expansion. The universe has no center. This tends to surprise people the first time they really think it through. If everything is expanding outward, surely there must be some central point, some original location where the Big Bang happened, with everything else flying outward from that single spot, like shrapnel from an explosion. But that's not how cosmic expansion actually works. And the balloon analogy, once again, helps explain why. Remember those dots scattered across the balloon's surface, drifting apart as the balloon inflated. If you were standing on any one of those dots, watching the others drift away, it would genuinely appear as though you were at the center, with everything else expanding outward from your own position. But choose a completely different, somewhere else on that same balloon, and the exact same thing would be true from its perspective as well. Every single, no matter where it sits on the balloon's surface, would observe every other dot drifting away from it, specifically. There is no special, central dot. No single point from which the expansion truly originates. Every location experiences the exact same pattern, simultaneously, equally, without any one position holding special, central status. This leads directly to one of the most quietly mind-bending truths about cosmic expansion. Expansion occurs everywhere simultaneously. It's not happening at some distant location, radiating outward toward us. It's happening here too. In this room. In the space between you and these words reaching your ears. In the space between every atom in your body, though at scales so impossibly small, and force is so comparatively weak that gravity and electromagnetic forces easily overcome it, holding matter together against the gentle stretching of space itself. Expansion is woven into the fabric of space everywhere, all at once, equally, without preference for any particular location. And this single fact, that expansion is happening everywhere, all the time, leads us towards something genuinely important for tonight's larger question, the one we've been gently circling since the very beginning of this journey. Because of expansion, reaching an edge becomes impossible. Think about what this actually means. Even if the universe does have some boundary, some far distant edge, sitting impossibly far away from us, the act of reaching it becomes a kind of cosmic impossibility, simply because of what expansion does to distance itself. New space continually appears between galaxies. As you traveled toward any hypothetical edge, more space would be continuously created in front of you, stretching the distance between you and your destination, even as you move toward it. It's a little like trying to walk toward a destination on a treadmill that keeps extending itself, just slightly faster than your own steady pace. For sufficiently distant points, this effect becomes so powerful that light itself, the fastest thing in existence, can never reach them. Space expands between us and those distant points faster than light can cross the gap, meaning some regions of the universe are not just currently unreachable, but will remain unreachable forever, no matter how much time passes. And this raises a profound, quietly humbling question. If expansion continues indefinitely, if space keeps stretching endlessly into the future, what does that suggest about the nature of the universe itself? Expansion may continue forever. Current evidence suggests this is genuinely likely. The expansion we've been discussing tonight isn't slowing down, gradually grinding to a halt the way one might expect gravity to eventually pull everything back together. Quite the opposite. Measurements taken over the past few decades suggest expansion is actually accelerating, driven by a mysterious force scientists call dark energy, a force we don't yet fully understand, but one that increasingly appears to ensure that this expansion will simply continue, indefinitely, into the deep future. It would be tempting, hearing all of this, to draw an immediate conclusion. If space keeps expanding forever, surely that means the universe itself must be infinite. But here, gently, the evidence asks us to slow down and resist that tempting leap. Expansion alone doesn't prove infinity. This distinction matters more than it might initially seem. A finite universe, including that closed, curved universe we explored earlier tonight, looping gently back upon itself like the surface of a sphere, could still expand forever. The balloon, after all, could simply keep inflating, indefinitely, without ever becoming infinite in size. It would remain, at every single moment, a finite, measurable, calculable size, just continuously, endlessly, growing larger. So expansion, as remarkable and important as it is, doesn't actually settle our original question. It doesn't tell us, conclusively, whether the universe is finite or infinite. It simply tells us that space is dynamic, active, continuously growing, regardless of whatever its true, underlying shape might actually be. It's a humbling thing to realize, after everything we've explored tonight. Even this, the discovery of cosmic expansion itself, one of the most profound revelations in the entire history of science, still leaves our original question quietly unanswered. The universe expands. Endlessly, perhaps. Carrying galaxies gently apart from one another, stretching space itself in every direction, simultaneously, everywhere, without center, without edge, without any sign of slowing down. And whether that expanding space is finite, curving back upon itself somewhere far beyond our observable horizon, or genuinely infinite, with no boundary anywhere, in any direction, at any scale, remains, even now, one of the universe's most quietly guarded secrets. There's one more chapter to this story, perhaps the most important one yet, because it brings together almost everything we've explored tonight: shape, curvature, expansion, and the deep history of the cosmos itself, into a single, unified picture. It begins with an idea so strange that, when first proposed, even many physicists found it difficult to fully accept. Inflationary cosmology strongly suggests immense expansion. This theory, known simply as inflation, describes something that may have happened in the very first fraction of a second after the Big Bang, a moment so brief, so impossibly short, that ordinary numbers struggle to capture it. In that fleeting instant, according to this theory, the universe didn't just expand. It expanded at a rate that defies ordinary comprehension, stretching space itself faster than light, doubling in size again, and again, and again, in a span of time smaller than anything we could ever directly perceive. It sounds almost unbelievable, stated plainly like that. And yet, inflation has become one of the most important, most carefully tested ideas in all of modern cosmology, because it elegantly explains several deep mysteries that puzzled scientists for decades: why the universe looks so remarkably similar in every direction, why its overall structure appears so smooth and evenly distributed, and, perhaps most relevant to tonight's journey, why space, on the largest scales we can measure, appears to be so close to perfectly flat. And this leads to something genuinely profound, when we connect it back to everything we discussed earlier about shape and curvature. Some inflation models naturally lead to infinite space. This is a remarkable conclusion, arrived at not through speculation, but through careful mathematics. If inflation truly happened the way these models describe, with space expanding by an almost incomprehensible factor in that first fraction of a second, then many versions of this theory suggest the universe wasn't simply stretched to an enormous size. It was stretched towards something closer to genuine infinity. Some inflationary models suggest that whatever finite patch of space existed before inflation began, it would have been expanded so dramatically, so completely, that the resulting universe would be effectively infinite in extent, or at the very least, so vastly larger than anything we could ever hope to observe, that the distinction between almost infinite and truly infinite becomes, for all practical purposes, meaningless. It's a humbling thought, when you really let it settle. The very same process that smoothed out the universe, that made it look so remarkably uniform in every direction we look, may also be the process that pushed its true size beyond anything we could ever directly measure or confirm. But inflation isn't simply a beautiful, untested mathematical theory. It makes specific, testable predictions about what we should observe when we look out at the universe today. And over the past few decades, scientists have tested those predictions, again and again, with increasingly sophisticated instruments. Observations indicate the universe is remarkably flat. This single finding, more than almost any other, has shaped how modern cosmologists think about the universe's true shape. Remember, flatness doesn't automatically mean infinite, as we explored earlier tonight. But it does rule out, fairly decisively, the kind of dramatically curved, tightly closed universe that some earlier models once proposed, a universe so curved that its overall shape would be obviously, measurably different from flat space. Instead, what scientists have found, through multiple independent lines of evidence, is a universe so close to flat that any deviation, if it exists at all, is almost too small to detect. This evidence didn't come from a single observation. It came from a series of increasingly precise missions, each one building carefully on the last, each one adding another layer of confidence to this remarkable picture. WMAP measurements supported this view. WMAP, short for the Wilkinson Microwave Anisotropy Probe, was a satellite launched in the early 2000s, designed to study the cosmic microwave background, that faint, ancient radiation left over from the universe's earliest moments, which we touched on earlier tonight. By carefully measuring tiny variations in this radiation, scientists were able to calculate, with remarkable precision, the overall geometry of the universe itself. And the results pointed strongly toward flatness, toward a universe whose overall geometry matched almost perfectly with the simple, flat space most people instinctively imagine, rather than the dramatically curved alternatives we explored earlier in tonight's journey. A few years later, an even more sophisticated mission added further weight to this picture. Planck observations strengthened it further. The Planck satellite, launched by the European Space Agency, studied the same cosmic microwave background that WMAP had observed, but with even greater precision, even finer detail, even more careful measurement. And its results, rather than overturning what WMAP had found, confirmed it, strengthening, with each passing year of data analysis, this same remarkable conclusion. The universe, on the largest scales we can measure, appears to be flat. Remarkably, almost suspiciously flat, to a precision that continues to astonish the scientists who study it. But the evidence for this picture doesn't rest on the cosmic microwave background alone. Other surveys, using entirely different methods, entirely different instruments, have added their own independent confirmation. BOSS measurements mapped cosmic geometry with high precision. BOSS, the Baryon Oscillation Spectroscopic Survey, took a different approach entirely. Rather than studying the ancient afterglow of the Big Bang directly, BOSS mapped the actual positions of millions of galaxies, scattered across vast regions of space, studying subtle patterns in how those galaxies are distributed. These patterns, shaped by sound waves that rippled through the early universe billions of years ago, act almost like a cosmic ruler, allowing scientists to measure distances, and ultimately, the overall geometry of space itself, with extraordinary precision. And once again, the results pointed toward the same conclusion. A universe close to flat, consistent with everything WMAP and Planck had already revealed. This same careful, patient mapping continues today, through ongoing efforts that build on everything that came before. The Sloan Digital Sky Survey continues refining our picture. This massive, ongoing project has spent years quietly mapping millions upon millions of galaxies, building an increasingly detailed three-dimensional picture of the universe's large-scale structure. With every new data release, with every additional galaxy carefully catalogued and measured, our understanding of the universe's true geometry becomes a little more precise, a little more confident, a little more refined. When you step back and consider all of this evidence together, WMAP, Planck, BOSS, the Sloan Digital Sky Survey, each one using different instruments, different methods, different approaches, yet all converging on the same fundamental conclusion: something remarkable emerges. Multiple observations point toward flatness. Not just one study. Not just one team, with one particular instrument, potentially subject to its own unique errors or biases. Multiple, independent lines of evidence, gathered over decades, using different technologies entirely, all quietly agreeing with one another. This kind of convergence, in science, carries enormous weight. It's one of the strongest forms of confirmation researchers can hope to find. And this returns us, finally, to the question that has been gently guiding our entire journey tonight. Flatness is consistent with infinity. We explored this idea earlier, but it's worth gently revisiting here, now that we understand just how strong the evidence for flatness actually is. A flat universe can be finite, as we discussed, through certain complex topologies, like that looping torus shape we explored a while back. But a flat universe can also, very naturally, simply be infinite, extending outward, endlessly, in every direction, exactly the way flat geometry most naturally behaves, without any need for unusual folding or looping at all. And when we combine this remarkably consistent observational evidence with the theoretical predictions of inflation, something quietly powerful emerges. Inflation and observations together make infinity plausible. Not certain. Not proven, in the way a mathematician might prove a theorem. But genuinely, scientifically plausible, supported by multiple independent lines of evidence, consistent with our best theoretical models, and aligned with decades of increasingly precise observation. It's worth resting here, for a moment, in this quiet convergence of evidence. After everything we've explored tonight, ancient philosophers wondering about the night sky, Einstein's revolutionary insights into curved space, the many possible topologies scientists have so carefully catalogued, the patient search for cosmic duplicates, the discovery of universal expansion, we arrive, finally, at this place. A universe that appears, through multiple careful, independent measurements, to be flat. And a flat universe that, quite naturally, leans toward being infinite. Not proven. Perhaps never fully provable, in any final, absolute sense. But plausible. Genuinely, scientifically plausible. And perhaps that's enough, for tonight. To rest here, beneath a sky that may truly extend forever, carrying within it more stars, more galaxies, more quiet stretches of darkness than any mind could ever fully hold, and to simply let that vastness settle over you, gently, like the most patient kind of peace. Given everything we've now traced together, the flatness measured by satellite after satellite, the predictions of inflation, the absence of any detected edge in any direction we've ever looked, it's worth pausing to notice where this evidence has been quietly leading us all along. Many cosmologists therefore lean toward an infinite universe. This isn't a fringe position, whispered by a handful of outsiders. It's a genuine, mainstream leaning among many of the scientists who have spent their entire careers studying exactly this question. Not certainty. Not consensus, in the strict sense we discussed at the very beginning of tonight's journey. But a real, considered lean, built from decades of careful observation, mathematical modeling, and patient, painstaking measurement. And this lean hasn't been weakening, as instruments improve and data accumulates. If anything, it's been doing the opposite. Current evidence increasingly supports that possibility. Each new satellite, each new survey, each refinement to our measurements of the cosmic microwave background, each new map of millions of galaxies stretching across the observable universe, rather than overturning the case for an infinite universe, has, again and again, quietly reinforced it. The flatness keeps holding. The absence of any edge keeps holding. And so, gently, year after year, the evidence continues to nudge in the same patient direction. But there's another thread to this story, one we haven't yet fully explored tonight, and it changes not just how we think about the universe's shape, but how we think about its entire future. It begins with a discovery that genuinely stunned the scientific community when it was first announced. In the 1990s, astronomers discovered expansion is accelerating. For most of the 20th century, scientists had assumed that cosmic expansion, even if it continued, should be gradually slowing down. After all, gravity pulls things together. Every galaxy, every star, every speck of matter in the universe exerts a gravitational pull on every other speck. It seemed only natural that this collective gravitational attraction should act like a brake, slowly easing the universe's expansion, the way a ball thrown into the air gradually slows as gravity pulls it back down. So when two independent teams of astronomers, carefully studying distant supernovae in the late 1990s, announced their results, the conclusion left much of the scientific world quietly stunned. The expansion of the universe wasn't slowing down at all. It was speeding up. Galaxies weren't just drifting apart, the way they had been since the Big Bang. They were drifting apart faster, with each passing era, as though some unseen hand was gently, persistently pressing on the accelerator of cosmic expansion itself. It was one of those rare moments in science where the data simply didn't match anyone's expectations, forcing an entirely new explanation into existence. Dark energy appears responsible. This is the name scientists gave to whatever mysterious force or property seems to be driving this acceleration. Dark energy. And it's worth being honest about what that name actually represents. It isn't a name born from deep understanding. It's almost the opposite. It's a name born from genuine mystery, a placeholder, of sorts, for something whose existence we can measure through its effects on cosmic expansion, but whose true nature remains, even now, deeply unclear. We don't fully know what dark energy is. We simply know that something, some property woven into the fabric of space itself, appears to be pushing everything apart, faster and faster, as the universe continues to age. And here's something that tends to startle people the first time they really absorb it. About 70% of the universe consists of dark energy. 70%. Not a minor component, tucked away in some small, overlooked corner of cosmic accounting. The dominant ingredient. The single largest contributor to the total energy content of the entire universe, and yet something we still cannot directly observe, cannot directly touch, and do not yet fully understand. It's a humbling thing to realize, when you really let it settle. Most of what makes up the universe, most of what determines its ultimate fate, is something science still struggles to fully explain. And dark energy isn't even the only mysterious ingredient in this cosmic recipe. Most of the remaining matter is dark matter. Dark matter is an entirely different mystery from dark energy, though the similar names sometimes cause confusion. Where dark energy drives the acceleration of cosmic expansion, dark matter is something else entirely, an invisible form of matter, detected only through its gravitational influence on galaxies and galaxy clusters, that appears to make up the vast majority of all the actual matter in the universe. We can't see dark matter directly. It doesn't emit light, doesn't reflect light, doesn't interact with light in any way our telescopes can detect. We only know it exists because of how its gravity shapes the rotation of galaxies, and the way light bends as it passes through regions of space where this invisible matter must be concentrated. Which leaves remarkably little room for the kind of matter we actually understand. Ordinary matter makes up only a small fraction. The atoms that build stars, planets, oceans, mountains, and every living creature that has ever existed, including every person who has ever paused to look up at the night sky and wonder about its true size. All of that, every star, every galaxy, every person, every grain of sand, accounts for only a small slice of everything that actually exists. A quiet minority, almost an afterthought, floating within a universe overwhelmingly dominated by two forms of energy and matter we still don't fully comprehend. It's worth resting on that thought for a moment, here in the dark. Everything you have ever known, ever touched, ever loved, ever seen with your own eyes, exists within just a small fraction of all that actually is. This picture, strange as it sounds, hasn't emerged from a single team's speculation. It has been carefully, repeatedly tested, through multiple independent surveys. Dark energy survey observations support this model. The Dark Energy Survey, a major astronomical project specifically designed to study this mysterious force, has spent years carefully mapping the distribution of galaxies, measuring the way light bends as it travels across vast cosmic distances, and tracking, with increasing precision, exactly how dark energy appears to be shaping the large-scale structure of the universe. And its findings, gathered patiently over years of careful observation, continue to align with this same broad picture, a universe dominated by dark energy, shaped significantly by dark matter, with ordinary matter playing only a supporting role. And remarkably, the simplest mathematical description of dark energy, one first proposed by Einstein himself, nearly a century ago, for reasons that had nothing to do with the actual discovery of cosmic acceleration, still fits the data beautifully. Einstein's cosmological constant still fits the data. This is a quietly remarkable piece of scientific history. Decades before dark energy was ever discovered, Einstein had introduced a mathematical term into his equations, called the cosmological constant, originally as a way to balance his own equations and produce a static, unchanging universe, an idea he later abandoned, reportedly even regretting, once Hubble's observations revealed that the universe was expanding after all. And yet, when scientists discovered cosmic acceleration, decades later, this same old mathematical tool, the cosmological constant Einstein had once introduced, then dismissed, turned out to describe the new data remarkably well. As though Einstein had, quite by accident, stumbled upon exactly the right piece of mathematics, for entirely the wrong reason, generations before anyone understood why it might actually be needed. So where does all of this leave us, as we consider the ultimate fate of everything we've explored tonight? If dark energy continues dominating, space may expand forever. This is the genuinely sobering, genuinely beautiful conclusion that emerges from everything we've discussed in this final chapter. If dark energy remains as it currently appears to be, a steady, persistent force, gently and continuously pushing space apart, then the expansion of the universe may never stop. Galaxies will continue drifting farther apart, faster and faster, for not just billions, but potentially trillions of years into the future, carrying the cosmos toward an ever colder, ever quieter, ever more spread out future. It's a strange thing, to end this part of our journey here, contemplating a future so distant that human timescales become almost meaningless beside it. And yet, there's something quietly peaceful in it too. Whatever the true shape of the universe turns out to be, finite, curving gently back upon itself somewhere far beyond our observable horizon, or genuinely infinite, stretching outward forever without any edge at all, it seems, increasingly, that its story will continue. Expanding. Stretching. Carrying galaxies, and stars, and quiet pockets of darkness, outward into a future as vast, and as patient, as everything we've explored together tonight. If dark energy truly does dominate forever, gently pushing space apart for trillions of years to come, then it's worth pausing here, in this quiet middle distance between everything we've learned and everything we still don't know, to ask one final question. Not whether the universe is infinite. We've spent this entire journey circling that mystery without quite arriving at its answer. But rather, if it is infinite, what would that actually mean? Not just for space itself, but for everything within it. An infinite universe would contain endless galaxies. Let's begin simply, with something almost easy to picture, compared to where this is about to lead us. If space genuinely continues forever, without any edge, without any final boundary, then the galaxies scattered throughout it wouldn't taper off at some distant point, fading gently into emptiness. They would simply continue. Galaxy after galaxy, cluster after cluster, supercluster after supercluster, stretching outward without any final count, without any last one waiting somewhere to mark the end of the list. And we already know, even within our observable universe alone, that this is no small number to begin with. The universe already contains at least trillions of galaxies. Trillions. Within just the 93 billion light-year bubble we explored earlier tonight, the portion we can actually see, actually measure, actually photograph with our telescopes, scientists estimate there are at least 2 trillion galaxies, each one containing, on average, hundreds of billions of stars. And if the universe extends beyond that observable bubble without any limit at all, if it truly is infinite, then that already staggering number of trillions becomes, quite simply, the beginning of an endless count. Not a large number. Not even an extraordinarily large number. An infinite one. This is where the conversation tends to take its strangest, most genuinely startling turn. Because infinity doesn't just mean more of everything we already know. It means something far stranger, when you follow its logic carefully, all the way to its natural conclusion. Infinite space may contain identical copies of you. It's worth sitting with that sentence for a long moment, because it sounds, at first, almost like science fiction rather than serious cosmology. And yet, this idea emerges not from speculation, but from careful mathematical reasoning, once you genuinely accept the premise of infinite space. Here's the reasoning, gently laid out. The number of ways that matter can be arranged, even across a region as large as our entire observable universe, is almost incomprehensibly vast, but it is not infinite. Atoms, particles, the fundamental building blocks of everything that exists, can only be arranged in a finite number of distinct patterns, within any given finite volume of space. But if space itself is infinite, if it truly continues without any limit, in every direction, forever, then you have a finite number of possible arrangements, scattered across an infinite amount of space. And when a finite set of possibilities repeats across infinite space, mathematics tells us something quietly extraordinary follows. Everything observable could repeat somewhere. Not just similar things. Not just roughly comparable things. Exact repetitions. Identical arrangements of matter, identical down to every atom, every particle, every precise configuration, occurring again, somewhere out there in the vast, unobservable reaches of an infinite cosmos. This isn't confined to abstract patterns of stars or galaxies. It extends to everything. Every planet. Every mountain range. Every quiet bedroom, every soft pillow, every person resting peacefully, listening to words very much like these, somewhere unimaginably far away, in a configuration of atoms so precisely identical to this one that it would be, in every meaningful sense, the same scene, repeated. Infinite replicas would exist beyond our horizon. It's important to say clearly, these replicas, if they exist, would lie far beyond anything we could ever observe, measure, or confirm. They would sit beyond our cosmic event horizon, in the same way we explored earlier tonight, regions of space whose light could never reach us, not in the entire remaining lifetime of the universe. This isn't something science could ever directly verify. It's a logical consequence, following naturally from the mathematics of infinity, rather than a claim anyone could actually test. But the reasoning behind it remains genuinely sound, and worth understanding a little more closely. Finite particle arrangements would eventually recur. This is the mathematical heart of the entire idea. Even though the number of ways particles can be arranged within any given region of space is staggeringly large, so large that ordinary numbers barely capture it, it is still, fundamentally, a finite number. There is an upper limit, however enormous, to how many distinct configurations of matter could exist within any specific volume of space. And if you keep sampling from a finite set of possibilities, over and over again, across larger and larger regions, stretching toward true infinity, eventually, mathematically, inevitably, patterns must begin to repeat. Not because the universe is trying to copy itself. Simply because there are only so many ways for things to be arranged, and infinite space provides infinite opportunities for those finite patterns to occur again, and again, and again. Every possible arrangement could happen infinitely many times. This is where the logic reaches its most genuinely staggering conclusion. It's not simply that patterns might repeat once, somewhere far away. In a truly infinite universe, mathematics suggests they would repeat infinitely. Not twice. Not 1,000 times. An infinite number of times, scattered across the endless reaches of space, each repetition as real, as complete, as fully formed as the original. It's almost too large an idea to comfortably hold, even after everything we've explored together tonight. And yet, it follows with genuine mathematical consistency, once you accept the premise that space truly never ends. This leads to perhaps the strangest implication of all, one that quietly reshapes how we think about probability itself. Improbable events become inevitable somewhere. Think about the most unlikely thing you can imagine. Some wildly improbable sequence of events, so unlikely that we'd normally dismiss it as essentially impossible. In a finite universe, such an event might simply never happen, anywhere, at any time. But in a truly infinite universe, with infinite space and infinite opportunities for even the rarest configurations to occur, that improbable event doesn't just become possible. It becomes inevitable. Somewhere. Eventually. Given infinite chances, even the most astronomically unlikely outcome is guaranteed to occur, not just once, but infinitely many times, scattered throughout the endless expanse of space. It's a strange, almost dizzying thought to rest with, here in the quiet darkness. And it leads some thinkers toward an idea that gently reframes how we might think about our own existence. Some argue life itself becomes less surprising in such a universe. If you've ever wondered at the remarkable improbability of life, the precise, delicate conditions required for a planet to form, for water to remain liquid, for the right elements to combine in just the right ways to eventually give rise to something capable of looking up at the night sky and asking these very questions, infinity offers a quiet, almost comforting reframing of that mystery. In a universe with truly infinite space, and therefore infinite opportunities for even the rarest combinations of circumstances to align, life, however improbable on any single planet, becomes, in some sense, less astonishing. Not because it becomes any less wonderful, but because infinite space provides infinite chances, and given infinite chances, even the most delicate, most improbable outcome eventually, and perhaps inevitably, occurs. It's worth letting all of this settle slowly, here at the end of this particular thread of thought, because it touches something genuinely profound about the nature of infinity itself. Infinity produces astonishing consequences. Not gentle ones. Not modest extensions of what we already understand. Genuinely strange, genuinely mind-expanding consequences, the moment you follow its logic all the way to the end. Endless galaxies. Endless repetitions. Identical worlds, identical lives, identical quiet moments like this one, occurring not once, but infinitely, scattered across a universe so vast that human imagination can only gesture toward its true scale, without ever fully grasping it. And perhaps that's the most honest place to rest, for now. Not in certainty. Not in proof. But in the quiet, humbling recognition that if the universe truly is infinite, then everything we've explored tonight is only the smallest possible glimpse of something far stranger, far larger, and far more wonderful than any single mind could ever fully hold. There's a question that naturally follows everything we've explored so far, one that pushes even beyond the question of whether our own universe is finite or infinite. Because some scientists have begun to wonder something even stranger. What if our universe, as vast as it is, finite or not, isn't actually the whole story? Some theories suggest a multiverse. This is one of the more speculative frontiers in modern cosmology, and it's worth approaching gently, with the same careful curiosity we've brought to everything else tonight. The idea of a multiverse proposes something genuinely difficult to picture. That our universe, with all its trillions of galaxies, all its 13.8 billion years of history, all the vast cosmic structures we've spent this entire journey exploring, might be just one universe, among many others. Multiple universes may exist beyond our own. Not simply distant regions of our own universe, lying beyond our cosmic horizon, the way we discussed earlier tonight. Something more fundamental than that. Entirely separate universes, potentially governed by their own physical laws, their own constants, perhaps even their own unique histories, existing alongside our own in ways that current physics struggles to fully describe, yet doesn't entirely rule out either. It's a strange thing to consider, here in the quiet. Not just more space, within the universe we already know, but possibly, more universes altogether. One of the ways physicists have tried to give this idea mathematical structure involves something called superspace. Higher dimensional superspace could contain our universe. This concept proposes that our familiar 3 dimensions of space, plus the 1 dimension of time we move through every day, might not be the complete picture. Some theoretical models suggest the existence of additional dimensions, beyond the ones we can directly perceive, forming a kind of higher dimensional space within which our entire universe might exist as just one small piece, floating among countless others. It's almost impossible to truly visualize, and that's all right. Even the physicists who work with these ideas mathematically often rely on careful equations rather than direct mental pictures, because human imagination, shaped entirely by 3-dimensional experience, simply isn't built to directly picture a 4th spatial dimension, let alone more. One particularly thoughtful version of this broader thinking comes from Roger Penrose, a mathematical physicist whose work has shaped cosmology for decades. Roger Penrose proposes a cyclic cosmos. Penrose's idea offers a different kind of answer to questions about beginnings and endings altogether. Rather than picturing the Big Bang as the single, unique birth of everything that exists, Penrose has suggested something quietly remarkable. One universe may emerge from a previous cosmic era. In this model, sometimes called conformal cyclic cosmology, the end of one universe, a future so distant, so cold, and so thoroughly stretched out by expansion that it becomes, in a strange mathematical sense, indistinguishable from a brand new beginning, could give rise to the birth of another. Our own Big Bang, in this view, might not be a singular, one-time event, but rather one chapter in an endless, repeating cycle, with universes ending and beginning again, in a rhythm stretching back and forward, beyond any single act of creation. It's a beautiful, quietly poetic idea, even if it remains, like so much we've discussed tonight, deeply uncertain. And remarkably, Penrose hasn't simply left this idea as pure theory. He's looked for evidence. Strange microwave background signals have been proposed as evidence. Penrose and his collaborators have pointed to certain unusual patterns within the cosmic microwave background, that same faint, ancient radiation we discussed earlier tonight, left over from the universe's earliest moments, suggesting these patterns might represent faint echoes from a previous cosmic era, somehow imprinted onto the radiation of our own. Circular patterns, subtle and faint, that some have proposed could be the gravitational signatures of black hole collisions, occurring in the universe that existed before our own. It's important to say, honestly and clearly, that this remains a genuinely controversial claim, even among scientists who take Penrose's broader theoretical work seriously. Most cosmologists who have examined this same data have not found convincing evidence for these patterns. But the search itself reveals something important about how science approaches even its strangest, most speculative ideas, not by simply imagining them, but by trying, wherever possible, to test them against real, measurable evidence. And Penrose's cyclic cosmos is far from the only place where scientists have looked for hints of something beyond our own universe. Some scientists see hints of larger realities beyond our universe. Various researchers, working from different theoretical angles entirely, have proposed other possible signatures, subtle anomalies in the cosmic microwave background, unusual patterns in the large-scale distribution of galaxies, mathematical inconsistencies that some interpret as faint traces of interactions with other universes, perhaps colliding gently with our own in the deep, distant past. None of these proposed signatures have been confirmed with anything close to scientific certainty. But their very existence, as topics of serious, careful research, reveals just how open this question genuinely remains, even among the most rigorous, most mathematically careful scientists working today. Which brings us to an important point of honesty, one worth holding on to carefully as we consider everything we've just explored. None of these ideas are confirmed. Not the multiverse. Not higher dimensional superspace. Not Penrose's cyclic cosmos, nor the circular patterns some have proposed as evidence for it. These remain, even now, genuinely speculative, serious, mathematically grounded speculation, pursued by careful, rigorous scientists, but speculation all the same. Nothing here carries the same observational weight as the flatness measurements, or the expansion evidence, or the cosmic microwave background data we explored earlier tonight. It's important to hold these ideas with open curiosity, rather than premature certainty. And yet, despite that uncertainty, or perhaps, in a strange way, because of it, they expand our imagination about infinity. These ideas matter, even unconfirmed, even genuinely uncertain, because they remind us just how much room remains, at the very edges of human understanding, for genuine wonder. They suggest that even the question we've spent this entire journey exploring, whether our own universe is finite or infinite, might only be the beginning of an even larger question. Not simply, does space go on forever? But perhaps, does reality itself go on forever, in ways even stranger, and even more vast, than space alone could ever capture? It's a question without an answer tonight. Perhaps without an answer for many generations to come. But it's a question worth carrying gently with you, here in this quiet, restful place, as we turn our attention back towards something a little more solid, a little more directly measurable, the largest structures scientists have actually been able to find, within the universe we can actually observe. Astronomers continue mapping enormous cosmic structures. Even setting aside every speculative idea about multiverses and higher dimensions, the observable universe alone continues to surprise us, revealing structures so vast, so genuinely enormous, that they stretch the limits of what scientists once believed was even possible. Vast filaments of galaxies, stretching across billions of light years. Great cosmic voids, almost entirely empty, sitting between them. Structures so large that, when first discovered, they quietly challenged some of our most basic assumptions about how matter could organize itself across the universe. And it's there, among these genuinely vast, genuinely confirmed structures, real, measured, mapped by patient astronomers over decades of careful work, that will continue our journey next. For now, simply rest here, in this strange and wonderful uncertainty. Somewhere beyond our universe, there may be other universes entirely. Or there may not be. Either way, what we know for certain is enough to hold a universe so vast, so old, and so quietly mysterious, that even its most basic, most fundamental question, whether it goes on forever, remains, gently, unanswered. Among everything astronomers have mapped across the observable universe, certain structures stand apart from all the rest, not stars, not galaxies, not even galaxy clusters, but something far larger. Formations so immense that they stretch the very definition of what a single structure can even mean. The Hercules, Corona Borealis Great Wall spans about 10 billion light-years. Sit with that number for a moment, because it's worth genuinely absorbing. 10 billion light-years. To put this in context with everything we explored earlier tonight, remember that our entire observable universe, that vast bubble surrounding us in every direction, measures roughly 93 billion light-years across. This single structure, the Hercules, Corona Borealis Great Wall, stretches across more than a tenth of that entire observable distance. It is, by some measurements, among the largest structures ever discovered in the known universe. A vast, sprawling collection of galaxy clusters and superclusters, bound together by gravity across distances so immense that light itself takes 10 billion years just to cross from one end to the other. When astronomers first identified this structure, many found it genuinely difficult to reconcile with existing theories. Cosmological models generally predict that matter should be distributed relatively evenly across the largest scales of the universe, clumped into galaxies and clusters, certainly, but without structures so disproportionately massive that they challenge the basic assumption of cosmic uniformity. The Hercules, Corona Borealis Great Wall sits right at the edge of what current theory comfortably allows, a quiet reminder that the universe still has the capacity to surprise even its most careful observers. And it isn't alone. Other vast structures have emerged from the patient work of cosmic mapping, each one adding another layer to this growing picture of unexpected scale. The Big Ring stretches across roughly 1.3 billion light-years. Discovered more recently than the Great Wall, the Big Ring presents its own particular puzzle. As its name suggests, this structure forms a vast, roughly circular arrangement of galaxies, spanning more than 1 billion light-years in diameter, large enough that, if placed in our own cosmic neighborhood, it would dwarf nearly every familiar structure astronomers have previously catalogued. Its enormous scale challenges assumptions about cosmic uniformity. This phrase carries real weight within cosmology, and it's worth taking a moment to understand why. The prevailing model of the universe, built carefully over decades of observation and mathematics, generally assumes something called the cosmological principle, the idea that, on sufficiently large scales, matter should be spread roughly evenly throughout space, without any single structure dominating an outsized portion of the cosmic landscape. Structures like the Big Ring, and the Hercules, Corona Borealis Great Wall before it, sit uncomfortably close to the upper limits of what this principle should actually allow. They don't necessarily disprove our current understanding of cosmology, but they do quietly stretch it, prompting scientists to ask careful, searching questions about whether our models of the universe's large-scale structure still need refinement. It's a humbling thing, in its own way. Even our most carefully constructed theories, tested and refined over generations, can still be gently challenged by the simple act of looking more closely and finding something larger than expected. Among all of these immense structures, one in particular has emerged as perhaps the most significant discovery yet. Quipu may be the largest reliably characterized structure. Named after the ancient Incan system of knotted cords used for record keeping, Quipu represents one of the most carefully studied superstructures astronomers have identified to date. Unlike some other claimed cosmic structures, whose true scale and significance remain debated among researchers, Quipu has been mapped with a level of care and statistical rigor that has earned it recognition as among the most reliably characterized of these enormous formations. It contains dozens of galaxy clusters. Each cluster within Quipu, on its own, would already represent an enormous gravitationally bound system, containing hundreds or even thousands of individual galaxies. And Quipu binds dozens of these already massive clusters together, into a single, interconnected superstructure, stretching across distances that dwarf almost everything else we've discussed tonight, with the exception of those very largest walls and filaments. Discoveries like Quipu, and the Big Ring, and the Hercules, Corona Borealis, Great Wall, all carry the same quiet lesson, repeated again and again throughout the patient history of cosmic mapping. Such discoveries remind us how little we've explored. Even within our own observable universe, the portion of the cosmos we can actually detect, actually measure, actually map with our most powerful instruments, we continue to find structures we didn't know existed. Formations so large, so unexpected, that they require us to revise our models, refine our assumptions, and approach the universe with a continued sense of humility, even after generations of careful, rigorous study. If structures this immense can remain hidden until relatively recently, simply waiting for our instruments and surveys to grow sophisticated enough to detect them, it raises a quiet, almost wondering question. What else might still be waiting out there, scattered across the vast regions we haven't yet carefully mapped? What other enormous, unexpected structures might still be hiding in plain sight, simply waiting for the right survey, the right telescope, the right moment of careful observation to finally reveal them? This sense of ongoing surprise isn't confined to large-scale structures alone. It extends to nearly every corner of modern astronomy, particularly since the arrival of one of the most powerful instruments ever built. James Webb observations continue revealing surprises. The James Webb Space Telescope, launched in the early 2020s, has fundamentally changed what astronomers can observe, peering deeper into space, and therefore further back into time, than any previous instrument. And in the years since it began operating, it has done exactly what great scientific instruments tend to do. It has surprised us. Some findings challenge existing assumptions. Webb has detected galaxies that appear to be more massive, more structured, and more fully formed than existing models predicted should be possible, given how early in cosmic history they actually existed. It has revealed details about distant atmospheres, ancient star formation, and the early universe's structure that have prompted genuine, careful reconsideration among cosmologists, rather than simple confirmation of what was already expected. This is, in many ways, exactly what good science should do. Not simply confirm existing theories, again and again, but occasionally, carefully, reveal the places where those theories need refinement, where our understanding remains incomplete, where the universe still holds genuine surprises in store for anyone patient enough to look closely. And after everything we've explored together tonight, ancient philosophers and modern satellites, curved geometries and expanding space, finite topologies and infinite possibilities, vast cosmic walls and rings stretching across more than 1 billion light-years, we arrive, finally, at the same honest, humbling truth that has been waiting quietly beneath this entire journey. Most of the universe remains unseen and mysterious. Despite every discovery, despite every careful measurement, every increasingly powerful telescope, every patient survey mapping millions of galaxies across billions of light-years. Despite the genuine, remarkable progress human curiosity has made, across centuries of careful observation, most of what the universe actually is, in its full and complete totality, remains beyond our current reach. Beyond our cosmic horizon. Beyond the limits of our instruments, our mathematics, and perhaps, for now, our understanding itself. So we return, gently, to the question that brought us here in the first place. all those hours ago. Space may be finite yet boundless. We explored this possibility carefully tonight, a universe curving gracefully back upon itself, like the surface of a sphere extended into 3 dimensions, or folding through more complex topologies, like that looping, donut-shaped torus we discussed earlier. A universe with a real, measurable, finite size, and yet, for any traveler exploring it, completely without edge, without wall, without any boundary ever to be found. Or, just as genuinely possible, space may be truly infinite, extending outward, forever, in every direction, without any limit at all. Supported by the remarkable flatness our satellites have measured, again and again, with increasing precision. Supported by the predictions of inflationary cosmology, suggesting space may have been stretched, in that first fraction of a second after the Big Bang, towards something genuinely without end. Both possibilities remain, even now, after everything we've explored together, genuinely open. Genuinely supported by careful evidence. And genuinely, honestly, unresolved. We may never know for certain. This is, perhaps, the most honest sentence we can offer, after this entire long journey together. Not a disappointing conclusion, but simply an accurate one. The true shape and size of the universe may remain forever just beyond our reach, hidden behind a cosmic horizon that even our most patient, most determined efforts may never fully overcome. Every observation reveals only a tiny portion of reality. This has been true at every single step of tonight's exploration. The observable universe, vast as it is, only a small window onto something potentially much larger. The cosmic microwave background, only a faint echo of the universe's earliest moments. Even the largest structures we've discovered tonight, the Great Wall, the Big Ring, Kipu, with its dozens of bound galaxy clusters, represent only fragments of a cosmos whose true, complete scale may forever exceed our grasp. And yet, rather than feeling discouraging, there's something quietly beautiful in that limitation, if you let it settle gently, here at the end of our journey together. The universe remains one of science's greatest mysteries. Not despite centuries of careful study. Because of it. The more carefully we look, the more precisely we measure, the more powerful our instruments become, the more we discover just how much remains unknown, waiting patiently beyond every horizon we manage to reach. This isn't a sign of failure. It's a sign of something far more wonderful, a universe so vast, so deep, so genuinely inexhaustible, that even our greatest efforts only reveal how much more there always is to learn. And so, here at the close of this long, quiet exploration, we return to where curiosity first stirred us to wonder. And somewhere beyond the farthest galaxy we can see, space may simply continue forever. Beyond the Hercules, Corona Borealis Great Wall. Beyond the Big Ring, and Kipu, and every structure astronomers have yet to discover. Beyond our cosmic horizon, beyond the reach of our telescopes, beyond anything human eyes will ever directly witness. Space may simply continue. Quietly. Patiently. Without edge, without end, without any final boundary waiting to be found. And there is something deeply peaceful and resting inside that mystery tonight. You don't need to solve it. You don't need to hold the entire universe in your mind, all at once, to feel the quiet comfort of its scale. You only need to rest here, now, beneath a sky that may truly never end, knowing that whatever the universe ultimately turns out to be, it continues, patiently, all the same, carrying within it every star, every story, every quiet moment of rest like this one, forever.